Buffers, which are sometimes called advanced aqueous equilibria, right? That sounds like a good time. Buffer is very simply a solution that resists changes to its pH. It can absorb both acid and base. So an effective buffer can have acid added to it, base added to it, and its pH will stay relatively unchanged. Relatively unchanged. So how do you make a buffer? Well, there's two ways to make a buffer, ladies and gentlemen. We got a weak acid mixed with its conjugate base. So that's what this top buffer would be showing. If we take a weak acid like acetic acid and mix it with its conjugate base, so some acetate salt, this is sodium acetate, but it could have been potassium acetate, lithium acetate, whatever. If we take a weak acid, mix it with its conjugate base salt, okay, we will create a buffer. Okay, this is a weak acid conjugate base buffer. You can also make a buffer using a weak base and its conjugate acid. So for example, the weak base ammonia, if we mix it with its conjugate acid, ammonium, so some ammonium salt, again, the chloride doesn't matter, that's a spectator ion. Here we will have a buffer as well. We have a weak base and its conjugate acid, ammonium. So how is a buffer able to withstand both acid being added and base being added, hydroxide being added? Well, let's look at this top buffer, and then we'll look at the bottom one. So let's imagine we add H plus to this top buffer. Here's how this works. For the top buffer, here's my acidic component, and then the conjugate base, acetate, that's my basic component. This top buffer has the acetate ions that would be capable of reacting with H plus. So if I add H plus to that top buffer, the acetate ions, so C2H3O2 minus, they're going to grab a hold of that and they're going to make more of the weak acid HC2H3O2. So I have something in the buffer, in this case acetate, that can be basic and absorb added H plus. But what if I add hydroxide? Well, if I add hydroxide, the acidic component of the buffer is going to react with it, HC2H3O2. And the acidic component of the buffer is going to pull the hydrogen is going to get pulled off, right? And then we will make more of the conjugate base acetate. Okay, we'll make more of that guy. How will the buffer? So you can see if I add acid, the one component of the buffer reacts. And if I add base, the other component of the buffer reacts. That's how a buffer is able to withstand both added acid and added base. Let's look at the bottom buffer here. If I add acid to this bottom buffer, the basic component of the buffer, the ammonia, is going to react with that. And we will make more NH4 plus, which actually goes to strengthen the buffer's ability to absorb base. If I add base to this bottom buffer, the acidic component of the buffer, the ammonium ion, will grab hold of the base and we'll make water and ammonia. So hopefully you can see it doesn't matter if it's a weak acid and its conjugate base or a weak base and its conjugate acid. Either way, you can absorb both additions of acids and bases to your buffer. So making a buffer, for example, here are some buffers. I could mix HF and sodium fluoride. That would be a buffer. We've got a weak acid and its conjugate base, fluoride, right here. We could do, again, the buffer that was on the other slide. Down here, we could have a buffer. We got a weak acid, carbonic acid, and its conjugate HCO3 minus. So this would be an effective buffer. If I took carbonic acid and sodium bicarbonate and I added more base, the acidic component of the buffer would react and it could absorb addition of base. If I added acid, H plus, the basic component of the buffer would react with it, and I would get water and H2CO3 minus. Awesome. Now, it is important, ladies and gentlemen, that it has to be a weak acid and its conjugate base, or a weak base and its conjugate acid. For example, this question is asking which of the following would make a buffer. A is not a buffer. Let's talk about why. Okay, we have a weak acid and a strong acid. Well, that just makes absolutely no sense, right? B, also not a buffer. Now, B, I think, would get a lot of students, they would get in trouble. They would say, well, that's an acid and there's its conjugate base. But here's the problem. HNO3 is one of the 6 strong acids that you need to memorize. So this would not be an effective buffer. Remember, the conjugate of a strong acid is not basic at all. So this really lacks a basic component. So that's why that one is not a buffer. If we look at C, we have a weak acid, but I need its conjugate base, nitrite. That doesn't have nitrite, so that's also not a base. D is going to be our buffer. We have a weak acid, and we have its conjugate base, nitrite, acting as a salt. You really got to memorize those 6 strong acids. HNO3 is strong. HNO2 would be weak. So you really got to know those 6 strong acids inside and out. If you haven't memorized them yet, get on that. Work on getting those down. Go ahead. Which one of these would make an effective buffer? Look through those. And hopefully you found that B would make an effective buffer. B would be a good buffer. A is not a buffer. It's a strong acid. Forget it. Get out of here. C is not a good buffer. That's a strong base. D is not a good buffer. That's a strong acid. This is a weak acid, but there's no conjugate base. It is B. We got a weak acid. We got its conjugate base, cyanide. Okay, as a salt. So that B, ladies and gentlemen, is your buffer. Hopefully you got that. All right, the common ion effect. This is really Le Chatelier's principle, okay? And predicting the pH of a buffer and where it's going to end up and all that good stuff. So if we take the pH of a 0.1 molar acetic acid solution, we get a pH of 2.9. If you get the pH of a 0.1 molar sodium acetate solution, remember that is a basic salt, okay? You get a pH of 8.9. So if I mix these two together, the weak acid and its conjugate base, you should predict that the pH is going to be somewhere between these two, somewhere between 2.9 and 8.9. Where does it end up falling? 4.7. 4.7 is what the pH ends up being. We're actually going to predict that. It's going to be 4.74. If you do a 1-to-1 buffer, we'll get there in a second. Let's see. Why does adding the conjugate base of a weak acid change the pH? We just talked about that. Really, it's kind of Le Chatelier's principle if you think about it. That's a weak acid. It's going to dissociate into H plus and C2H3O2 minus. If I add conjugate base, it shifts away. So the weak acid won't dissociate as much, and that's why the pH goes from 2.9 up to 4.7. So it's kind of like Le Chatelier's principle. Okay, so what will happen to the equilibrium position when that is added? We said it shifts backwards, the Chatelier's principle. This is called the common ion effect. We're going to go right to the Henderson-Hasselbach equation. So there is a shortcut that we can take here, ladies and gentlemen, for a buffer. And the first thing I want to mention is that you are only allowed to take this buffer shortcut called the Henderson-Hasselbach equation if you're able to assume that x is small. The Henderson-Hasselbach equation only works if x is small. And here's how it works. Okay, if we write the mass action expression for a weak acid, and then if we rearrange it to get H3O plus equals. So if we, divide, if we multiply both sides by HA and then divide by A minus, okay, we can rearrange this equation to get H3O plus equals Ka times HA over A minus. And then what we can do is we can take the negative log of both sides. And if we take the negative log of both sides, remember you can do anything to an equation as long as you do it to both sides. If we take the negative log of both sides, we end up with a pH on the left. And then we're going to get pKa right here. So let's go to the next slide. So we end up with, a negative log of H3O plus, negative log of that. Remember, when you multiply logarithms, you actually add. So that's what they did here. And what we end up with is the negative log of H3O plus, that's pH, negative log of Ka, that's pKa, and then we get the log of the base concentration divided by the acid concentration. And this, ladies and gentlemen, is our Henderson-Hasselbach equation. Now, I will give that to you on a test. You don't have to memorize the Henderson-Hasselbach equation. They actually give that to you on the ACS final, and they don't give you a whole lot of equations on the ACS final. But you want to write that down and circle it. You're going to be using that Henderson-Hasselbach equation quite a bit. Now, this is the Henderson-Hasselbach equation for a weak acid and its conjugate base buffer. Okay, weak acid and its conjugate base buffer. Whoa, what happened? If we want to do a weak base and its conjugate acid buffer, that's going to be a totally different formula. So I wanted to use that formula to predict the pH of a 0.1 molar acetic acid, 0.1 molar sodium acetate buffer, if the Ka of acetic acid is 1.8 times 10 to the negative fifth. So give me a second to write all this down. So here we go. We're going to use, we recognize this is a buffer, weak acid conjugate base. If you can make the X a small assumption, it is fair to use the Henderson-Hasselbach. So take your lowest initial concentration divided by K. It's going to be greater than 500. We can use the Henderson-Hasselbach to solve for pH. pH equals pKa plus the log of the base concentration over the acid concentration. We need to get a pKa. So pKa equals negative log of the Ka. So the pKa here is going to be 4.74. It's my pK. So pH equals 4.74 plus the log of the base concentration, 0.100, over the acid concentration, 0.100. And here's where we have a special scenario. This is what we call a one-to-one buffer. 1 part acid, 1 part base. And when you have a one-to-one buffer, something special happens. Okay, this is going to be the log of 1, and the log of 1 is 0. So in a one-to-one buffer, the pH equals the pKa. In a one-to-one buffer, the pH equals the pKa. That's a special scenario. That only happens if the conjugate base and acid concentrations are the same. Now I want to try another one. So here we have another buffer. This is a benzoic acid sodium benzoate buffer. You can see, excuse me, this is not a one-to-one buffer. I want the pH of this. Here's your acidic concentration. Here's the conjugate base concentration. I want you to try to use this newfangled Henderson-Hasselbach equation. I give you the Ka of benzoic acid. Can you get the pH of this benzoic acid sodium benzoate buffer? Go ahead. All right, let's see how you did. So the Henderson-Hasselbach's pH equals pKa plus the log of the base concentration, that was the sodium benzoate, divided by the acid concentration, benzoic acid. So first thing, we need to get a pKa. So pKa equals the negative log of 6.5 times 10 to the negative fifth. Negative log is 6.5 times 10 to the negative fifth. The pKa equals 4.19. pH equals 4.19 plus the log of the A minus ion concentration, 0.150, divided by the acid concentration, 0.050. So 4.19 plus the log 0.15 divided by 0.05, and we get 4.67. That is our pH, 4.67 for this weak acid strong base. I'm sorry, weak acid conjugate base buffer. How'd we do with that one? We get 4.67. Shouldn't be shocking. If it was a 1-to-1 buffer, we should get 4.19. But we have more base than acid, so it should be more basic than 4.19, and it is. It's 4.67. So it's more basic than the 1-to-1 pH would be. Try this one out. What must be true? If a buffer contains a weak acid in its conjugate base, and the buffer has a pH of 4.25, but the pKa of the weak acid is 4.82, which of those statements must be true? Once again, if it was a 1-to-1 buffer, the pH would be the pKa, but we are more acidic than the pKa, which means ding, 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 there's more acid than base. This is essentially the opposite of what we just looked at. If we look at this problem we just looked at, here we had more base than acid, so the pH was higher than the pKa. In the problem that's on this slide here, the pH is lower than the pKa, so there must be more acid than base.